So every year, most recyclable steels ends up in landfill, not because they can be reused, but because they get mixed with general garbage. Once contaminated, they can't be processed, and valuable materials like plastic, paper, metal, and other are waste. That made us wonder, what if a sorting could happen automatically, right at your home? That question becomes our foundation for the project, the Smart Trash Can AI.
The system runs on a combination of hardware, AI, and cloud technology. A Raspberry Pi runs the AI detection model, while an Arduino Nano handles all the components, the servo, stepper motor, and infrared sensor. We trained the detection model on RoboFlow, using YOLO V8 as the base architecture, then fine-tuned it with hundreds of images of bottles, cans, and wrappers. The Pi is programmed in Python, the Arduino in C++, and they communicate via serial connection. On the software side, our Next.js frontend and Node.js backend connect to Supabase for database storage and authentication. The system also integrates OpenAI's API to further analyze each captured object and uses WebSockets so data updates live across all devices without refreshing. The AI training was the first big hurdle. We spent almost 2 weeks experimenting, adjusting datasets, annotations, and lighting conditions. Early versions misdetected backgrounds or missed items entirely. It was frustrating, but each failed model taught us what good data really means. Once we improved dataset balance and exposure, accuracy jumps significantly.
Other than the AI challenges, we also face hardware integrations challenge. The servo stepper motors behaved unpredictably at first, sometimes spinning endlessly and skipping steps. We realized that the power supply was unstable, so we added capacitors to it, adjusted timing delays, and rewrite the control sequence. That finally stabilized the entire movements.
One major challenge we faced was the initial design of the bin. We needed a structure that looks modern, used minimal 3D printing, and was sturdy enough to hold components while keeping the wires not too exposed. We first considered using wood for strength, but it made wiring and creating a top opening difficult. We also had to design a roof for the camera and compartments that allow easy trash bag replacement without affecting the bin's movement. Building the bin's body was another pivot. We planned to 3D print every part, but the printing time and fragility makes it unrealistic. So we redesigned the frame using metal poles and acrylic panels, which is faster, sturdier, and cheaper.
So even after all of these integrations, we still face smaller issues. There were serial delays between the Pi and the Arduino. There were camera's lag and model confusion with reflective materials like aluminum. Each issue actually forced us to debug, test, and refine the item.
What went right was the coordination between hardware and AI. Once tuned, the system worked smoothly, recognizing and sorting items with impressive speed. What went wrong initially were timing mismatches, power fluctuations, and inconsistent lighting that threw off detection.
But all of the challenges become the best part of the process. It teaches us how to problem solve, do a lot of iterations, and actually every failure moved us one step ahead closer to a real working prototype.
The project taught us the full journey of making, from data training, coding to mechanical calibration and user experience.
And more than anything, it shows us that innovations is built on persistence, adaptations, and curiosity.